Okay, so we're going to be using problems now that involve meters. So we're going to need a metric unit. We can't use the American. So before we had a delta equals to 62.5 pounds per cubic foot. And so what that meant was that, it's not pounds, pounds, there we go, per cubic foot, is that we had this little cube, right? And it was 1 foot. And so that means it weighed 62.5 pounds. So we need that same kind of unit, because then we took this, right, and we multiplied it by the volume to give us the entire force. And that gave us the pressure at the bottom by dividing by the area. So now we need our delta for metric. So what you have to think is, how much does that little block weigh? And so that's its force. That's mass times acceleration. And since we're talking about weight here, it's mg. So that little block now, and we're going to be using meters. So it's a little bit bigger. Well, it's 3 times the length. That's now 1 meter. And so we want to see what its weight is. So how much does that one block weigh? That's 1 meter by 1 meter by 1 meter. So we need the mass. So the mass is 1,000 kilograms per cubic meter. And then we have to now apply some sort of force to it. Make it a force. We need the acceleration, which is our gravity, which is 9.8 meters per second squared. And what this gives us is 9,800 newtons per cubic meter. So what a newton is a newton is a kilogram times meters per second squared. So it's how fast you can accelerate 1 kilogram by 1 meter per second in a second. Got it? All right. So we get 9,800. So that's our new delta that we're going to be using. So we can use the same thing as before. Our force is the pressure times acceleration, and our pressure is our delta D. That's our pressure times the area. So it's our pressure is our delta times the depth, and it tells us our pressure at that amount. Remember, the A will just cancel if you try to make the pressure. So it's just delta D. Okay. So, by the way, this right here is your rho. If you look up the mass, they'll use the symbol rho for 1,000 kilograms per meters cubed for the mass. I mean, for the mass, 1,000. All right, so let's try a problem. So on this one, you can see now we're dealing with a circle, not a rectangle. So this is not something that we can calculate. This rectangle that we draw here is not something that we can calculate. There's an issue here when it printed. I'm not making another video. I don't have time to go back. So we're going to just move it here. That's now x, and that's y. So what you have to do is now use a coordinate axis, because this is actually a curve here with a function. So it's not just a nice straight line that we're going to be dealing with. So now we would have dy for the thickness, and we'd have to use x equals. Okay, but before we do that, let's label our numbers. Since we know this is x, that would make this 0, and this is 4. And this would be our y, because we are now on the y-axis. So our rectangle is at a location of y. The water is at a height of 4. And the bottom is at 0 here. All right, everything's set up. So now we just need to plug everything in. So we're going to need a delta, which we already know. We'll just leave it as delta and plug it in at the end. Let's change that back. So our delta. And then now we need a depth. So let's see, how far is this rectangle down? So this would be representing our depth. So if you look at it, it involves the letter y and the number 4. So how do you find the distance? You just subtract them. So our depth here would be 4 minus y. So we can plug that in now. 4 minus y. Now we just need the area of our rectangle. So again, we're just looking at how much pressure is being applied to this little rectangle, right? So if we know the pressure being applied here all the way across, and we add them all up, it tells us the total force. So how much force is being applied to this rectangle as pressure? And so we need to find our area. So it's whatever x equals and dy. So this is a circle. So circles are x squared plus y squared equals r squared. So all I have to do is go back to our little dome here that's partially floating. And we look and see, okay, well, if it's a diameter of 12, our radius would be 6. So this is x squared plus y squared equals 36. So now what do you solve for, x or y? Well, you just look at our rectangle. It says we have to solve for x because we have dy. So x equals square root 36 minus y squared. And we're using the positive because we're using this side. So It would go all the way down here if we were fully submerged, but it's not. It's going to stop at the 0, but that'll take care of it when we do our y's. So you're going to be plugging in the y of 0 and the y of 4. If we had to go all the way down, and then we'd be going from our -6 all the way up to our y of 4, but we're not. So here we go. So now we have our depth, perfect, and we have our area. That would be the square root of 36 minus y squared dy. So let's write that out. Our area here would be square root of 36 minus y squared dy, because remember it's just length times width. So we have a length of square root of 36 minus y squared and a height of dy. Now we just need to take and add up all of those rectangles. So right now we're just here, right? That's just one of them. So that would be a y of a certain value, and we're going to go from the bottom all the way up to the top. Right? Does it matter if you go to the top or the bottom? No. Bottom to the top? No. They both add up. But we want to start with a y of 0. So even though it's the farther depth down, it's going to plug it back in because we did 4 take away 0. So that's a depth of 4. So 4 minus y was our depth. It's going to work perfectly fine. If you then plug in the y value, it will tell us the length of this. The width is dy. Everything will plug in perfectly. So if we were to plug in, say, a y of 1, the depth would be 3. Plugging 1 in would give us 36, square root of 36 minus 1 squared. That would give us our length. And then the width would be dy. It would give us the force at this one. And again, our delta x is approaching 0. So everything is going to work out perfect. So there we go. Now we just do our integral from 0 to 4, delta 4 minus y, square root 36 minus y squared dy. And again, our delta is just the weight of that one tiny little cube, right? The 1 meter by 1 meter by 1 meter with gravity being pushed against it is 9,800 newtons per cubic meter. So that's all this is. And so this is calculating that rectangle for us as well with the depth to give us our dA. Okay, so now all I have to do is plug that in our calculator and see what it gives us. So our delta was 9,800 times math 9. There's our integral from 0 to 4, and then 4 minus, we'll use x. You can use y if you want. Doesn't really matter. You just pick a letter. Just like over here, you could have made this the x-axis and that the y-axis. Would have worked fine. Dx. Now, if you notice, this is only this half. So what we're going to have to do at the end is double it. So times 2 now gives us both. So it's 90, we'll just say 90,04181. We'll start there. 90,04181. And then the answer is in newtons. So we have to put a 2 in front. A 2 in front for each of these because we are doubling it for both sides. Now, why is it newtons? Well, let's look at our units here. Our delta, right, would be newtons per cubic meter. Our d would be in meters. And our area, since it's an area, would be meters squared. So you see they just cancel, giving us just newtons. So that's the amount of force we're applying, which is newtons. All right, let's try it again now, just because it's nice to have two, with a fully submerged one. Okay? So it's going to work exactly the same way. This is x, this is y, and we've centered our origin at the center of the circle so that we can use our nice clean circle formula to create a circle. Because remember, whatever function you have, it needs to look just like this wherever your x and y are. You can't just shove this as the axis up there, then you'd have to shift this down, which is fine. Works completely fine that way. All right, so let's look at everything. Right here would be 0. It has a radius of 8, which means up to here would be 8. This would be -8. And at the top, we have to add another 4. So that would be 12. So there we go. So that would be 8, -8, 0, and then 12 is where we are. And then this is where we're going to place our y, because that's where my rectangle is drawn. You just have to draw a rectangle. You can draw it down here if you want, or here, it doesn't matter. But the thickness would be y, and again, we have to solve for x. So our equation would be x squared plus y squared equals 8 squared. So that would be solved. It would be x squared plus y squared equals 64. And again, you have to solve for x. So 64 minus y squared. And like I said before, that's going to give us this side only. So that's what that equation gives us, which means we're going to have to double it just like before. So let me plug that in over here. All right, so our force again is pressure times area, which is our delta D times A. So we need our depth. Our delta is given. We already know it's 9,800. Our depth is what we need. So where's my y? It's here. So as I move this up and down, my y is from here, but how far below is it? Well, this is the depth of my rectangle. So that means it's from, it's horrible. Let's try that again. There we go. My depth is from 12 to y. So it would be 12 minus y for my depth. Now for the area, it's just like before. My area here would be square root of 64 minus y squared dy, because again, it's length times width. Okay, so that would be the force applied to this. It's the pressure times that area, right? It's our pressure times the area that we have here. You can kind of think of all these little things just pushing against there with a certain pressure. Okay, so now we do our integral. So our circle starts at -8 and goes to 8. Let's look at this with Desmos. So we're going to go from 8 to -8, or from -8 to 8. All those rectangles will add up. So the bottom one is going to have to go from -8. So again, you can think about it that way. We have this all the way up here at 12. And so 12 take away 8 would be a depth of 20 because it's a -8. So our formula is going to work perfect. That would be a depth of 20 with that rectangle area. And then if we went to 0, that would be a depth of 12 times that rectangle, right? So everything should work out perfect. So again, we're going from -8 to 8. And if you've already drawn your little thing here, you can already see my circle starts at -8, ends at +8. And so now we just have to plug it in. Delta 12 minus y, square root 64 minus y squared dy. Let's plug that in our calculator. So we have 9,800 times math 9. We're going from -8 to 8. And then 12 minus y. Second square root 4 minus y squared dy. Hit enter. And we get this. Now, again, we have to double it because that's only half. So we really have that. So 2236. Double check that. And then again, this is newtons. So let's do a little scientific this time. 3, 3, so 7. So we'll do 2.4 times 10 to the 7 newtons. Okay, so you can see they're very similar. So if you can make a function for one of the sides, go for it. But you'll be using dy because of the x and y axis. That they're both set up the same thing. So all we really do is change it. So whether it's partially submerged, you just go from 0 to 4, wherever you put that. And if it's fully submerged, same exact thing. So these are both situations that you're going to run into. And if it's not, and you can actually draw a straight line that makes a perfect rectangle, then do it in terms of x because it is a little bit simpler, like in the previous video. Oops, almost forgot. Since we did double it, we do need to put a 2 next to these. Perfect. So now that we've doubled that. So again, you can always do this the half side and then double it.